Hey everyone, I am following along with the common theme so far. I am exhausted. I am just going to re-summarize everything from the beginning till now, and today's just going to be another one of those filler episodes. So starting with this, the next task, the lesson 11, was all about eigenvalues and eigenvectors, right? And essentially the task was to use NumPy's linear algebra module to compute eigenpairs of a symmetric matrix, and then optional advanced implement the power iteration method. And you guys knowing me was like, fuck using a library. I'm gonna figure out how to do this from scratch, right? So I put this in here. I immediately asked to follow up on that first step, right? Started getting confused. And at that point, I was just like, okay, wait, before I continue, let me figure out what eigenvalues and eigenvectors were specifically. And specifically, what they are is a symmetrics real matrix that is square, right? That represents a linear transformation. Any such matrix will have eigenvectors, and an eigenvector is essentially when you apply, is defined by when you apply that transformation to an eigenvector, you will get the same vector scaled, um, and the scalar is the eigenvalue, right? Um, and specifically to rewrite that equation of AV equals lambda V, lambda being eigenvalues, V being the eigenvector. If you rewrite that equation, A minus lambda IV equals 0, um, you need A minus lambda I to be singular. So one of the characteristics of a matrix, um, wait, no, never mind. And anyways, if you expand the determinant of A minus lambda I, because it has to be singular, um, why does this need to be singular? Oh. Mm. Any matrix with a non-trivial null space is singular. What the hell is a null space? Also known as the kernel, is the set of all vectors that, when multiplied by the matrix, result in the zero vector. Okay. Any matrix with a non-trivial null space is singular. Null space is the set of all vectors that, when multiplied by the matrix, result in the zero vector. Okay. Okay. And the geometric intuition of this is essentially that, since it's obviously just scaling the same vector, greater than one it expands, less than one it shrinks, sign flips, it'll change direction, right? It's pretty straightforward as to what it is, why it's valuable, why are eigenvalues and eigenvectors useful? I don't know, let's put it that way. Eigenvectors make understanding linear transformations easy. They are the axes, directions, along which a linear transformation acts simply by stretching slash compressing and or flipping. Eigenvalues give you the factors by which this compression occurs. The more directions you have along which you understand the behavior of a linear transformation, the easier it is to understand the linear transformation. So you want to have as many linearly independent eigenvectors as possible associated to a single linear transformation. Okay, I'm gonna read this some other time, but yeah, I need to get into that. So then after that, basically we came and dived into like how are these eigenvectors made? I got hit with this, got confused because I didn't quite understand this equation. And so I followed up on that. So the equation essentially com has these things going for it and or these components. So A, as we already discussed, the symmetric matrix. Q is the orthogonal matrix or orthonormal, where the columns are eigenvectors. Are all eigenvectors orthonormal? Oh, okay. So not all eigenvectors are always orthogonal. Um, The matrix is symmetric, symmetric meaning that the matrix is equal to its transpose. Then its eigenvectors corresponding to distinct eigenvalues are indeed orthogonal. Okay, yeah, fair. So Q is the matrix of eigenvectors. Uppercase lambda is the diagonal matrix of eigenvalues. So it's a matrix of the same shape where all the diagonals are the associated eigenvalues for the eigenvectors. Um, QT is the transpose of Q, and since Q is orthogonal because it is the matrix of all the eigenvectors, and all the eigenvectors, um, what do you call it, of a real symmetric matrix will be orthogonal. So therefore, the transpose of Q is the inverse because the inverse of a matrix that has all orthonormal vectors is its inverse is defined is the transpose, and I is the identity matrix, right? So QTQ equals I. Okay, fair enough. That's the same as saying A inverse A equals I. That's true always, basically. Q lambda, we thought this one through. Q lambda is essentially um, multiplying each vector with its associated eigenvalue, and then A equals Q lambda QT, which is essentially the sum of the outer products. That's another thing that we dug into a little bit in the last episode is the difference between inner products and outer products. Inner products are essentially your dot products, and essentially how you do the products for a vector. It follows similar rules as matrix multiplication, where you multiply rows times columns. So an inner product or the dot product is very specifically defined as the transpose of the vector times the vector itself, but times the second vector, right? So transpose of v1 times v2, basically, right? So that means the first vector will be horizontal or a row, and the second vector will be a column, and you just chuck chuck and you get one value, right? Whereas with the outer product, it's flipped. You do the v1 vector 1 times the transpose of vector 2. So v1 is the column and then it's the row. So each row in the first vector times the column, row, column. And then you go to second row, column, second row, column, second row, column, right? So whereas with the inner product you yield a value, with the outer product you yield a new matrix, essentially. And we figured out that this statement is true, and that's basically where I got to last time, and I want to try and push it so bad, but I'm also so tired today. It's unreasonable how tired I am. So I'm gonna call this episode recap, I guess. I'm just gonna call it, I don't know what I'm gonna call it, whatever. I'm gonna put some bullshit clickbaity title. See you guys in the next one. Have a great one.